Hi, welcome to another lecture of Design and Application of Lasers. I'm your instructor, Dr. TJ Hammond. This is a lecture for Friday, October 2nd, where we continue on with Chapter 4, Laser Oscillation, Gain and Threshold. So why are we covering Chapter 4? Or what are we covering in Chapter 4? The main points of this are that we want to understand amplification and we want to understand stimulated emission. And it turns out that these things are intricately related. So we want to make bright lasers, so we require amplification. We want this process to be coherent. That requires stimulated emission. The daily assignment will be deriving equations 4.11.1 in Maloney for Monday, October 5th. Okay, so recall, we discussed last week when we have a driven damped harmonic oscillator, we end up with an absorption. And this absorption depends on the rate of damping. And so this damping could be whatever it is, but we modeled it simply as something that's proportional to the velocities, like so some kind of drag. Now we go through this and we find that we get a complex amplitude of this oscillation where there's a real part, and we find that real part leads to the index of refraction and dispersion, and then we have this absorption part, or this imaginary part, and that leads to absorption. So if gamma is very small, that means that this thing approaches 0, then this line width here is very, very narrow. And that also means that this lifetime is an extremely long-lived state. In the limit that gamma goes to 0, then this thing becomes a delta function, and unless if you're exactly on resonance, you won't get any absorption at all and nothing will happen. Okay, I wanted to kind of emphasize that because some people had kind of said something in the daily assignment that seemed a little misleading. So if there were no gamma, if there's no damping coefficient, then nothing gets absorbed because we can never be exactly on that resonance. So if we remember from what we were discussing on Monday and Wednesday, what are the cavity requirements? Well, we have some energy source, and that's going to be pumping this crystal. This crystal is going to have some characteristic that it can convert that pump energy into light. And then it will emit these photons, and these photons will go off in any direction. And so in order to have some positive feedback for this system, we need to have highly reflecting mirrors to contain these photons so that we can have these things rattle back and forth and continually get gain through stimulated emission. So threshold gain, the minimum amount of gain that we need to get the system to work, is going to be given by -1/2L, where L is the length of the gain, and then the log of R1 times R2. So basically, it's like dependent on the loss of this cavity. So if these mirrors are really close to 1, then our threshold gain, our minimum gain for this system even turning on, will be close to 0. Okay, and the more loss that we have, the more gain we need in order for this thing to be stable or reach steady state. Okay, this week we've also talked about the photon rate equation. So we're pumping these ground state electrons up into some excited state, and this excited state is some kind of metastable state. So this electron is kind of sitting in this excited state, or this atom is sitting in an excited state, until a photon comes along, and this photon interacts with this electron with some probability, and that probability is dependent on the cross-section here, sigma. And so the probability of these things interacting, if it does interact, then this electron drops down to the ground state, and out comes 2 photons, because this photon had the same energy as this energy, the difference in the energy of these 2 states. So whenever I'm drawing these states as like state 1 and state 2, like this, the vertical axis is always implied to be energy. This cross-section, the probability of this electron interacting with this photon is material dependent. Yeah, and as I said, it's given as the cross-section. Okay. So we also discussed when we were talking about the two-level systems that it turns out that if you have this photon here, the thing is that this photon exactly matches this energy here. And it turns out there's this thing called Fermi's golden rule that you derive from quantum mechanics that basically says, well, if there's a certain probability that this photon de-excites this electron from the upper state down to the lower state, there's the exact same probability that this photon will excite this lower state up back into this upper state. And so it turns out that if you have a exactly two-level system, you can never get population inversion, because if you have this lower level system, then this photon will excite to the upper state, and then eventually, you'll have these excited metastable states, and then you have a whole bunch of photons in your cavity, but all those photons in the cavity will de-excite this upper state down to the lower state. And so the best you can do in that case on average will be 50% upper state and 50% lower state, and then that means you don't get population inversion. And so we need to do something else. We need to trick this system in order to be able to have population inversion. And that's where we come into these laser schemes. So what we need to do is somehow trick the system into being in an excited state, but that rate, but these excited states don't have the exact same energy transition from the pumping laser as we do, or from this pumping energy source as we do from this laser transition. So if we had this as a light source, we have some energy that's exciting, some photon that's exciting from state 1 to state 3, and then we quickly decay from state 3 down to state 2, and then we have this electron in this metastable state, and we can have a photon coming along, and that can de-excite this excited state, and out come an amplification of photons. And so basically what we've done is we've changed this cross-section. Our pumping energy, our pumping photons are not talking to state 1 to state 2. Our pumping photons are only talking state 1 to state 3. And this laser transition and all these amplified photons are talking with state 2 to state 1. And so because they don't talk to each other, because there's this intermediate state, we can have this population inversion. So this is the most basic setup for a laser. The requirement in order to have population inversion is a 3-level laser. It turns out that we also look at 4-level lasers, and the reason for that is because they're actually slightly more efficient. And so if you have, instead of having just a ground state, you actually have this 0th state, which would be our ground state, and we couple from the 0th state up to the 3rd state. And so then this upper state has a fast decay, and then the 2nd state is a metastable state, or it's a long-lived state. And then a photon comes down to stimulate this emission. We have this laser transition, and then instead of dropping to the ground state, it drops down to this 1st state, and then there's some fast decay to a lower state, to the actual ground state. There's a subtle difference between these two systems. You would think, okay, what's the difference? If this is just a fast decay here, how is this really going to change it? Well, we'll go through the math and we'll show that the power requirements, or the pumping requirements for the 4-level system are less than it is for the 3-level system, which is why we're interested in them. Of course, you can have more energy levels. Like this could be a whole bunch of energy levels up here, and you wouldn't call this a 6-level energy system. Or energy laser, because all these states will be fast that come down here. And so basically, if there are a whole bunch of states up here, we just call it a 3-level laser. And if there are a whole bunch of states up here and a whole bunch of states over here, we still call that a 4-level laser. Okay, so for a 3-level laser, we pump out of state 1 up into state 3. And that's given here by these differential equations. So from 1 to 3, and then we assume a very fast decay process. So that means that the rate of change of level 2 is approximately equal to the rate of change of level 3. All right, and so then effectively we end up looking at this like a 2-level laser, but what we saw from Wednesday's lecture is these photons, these pumping photons, don't cause the stimulated emission, and so that allows us to have this population inversion. So we now have effectively a two-level system. We can get this coupled first-order differential equation. And of course, we're going to assume that the third state basically is very, very short-lived, and so we're going to approximate that all the states involved are going to be just n1 and n2, so the rate of change of n1 and n2 is going to be 0. And that's going to be a conservation of states or conservation of energy and electrons and all that kind of stuff. As I said, the total number of states are approximately going to be n1 plus n2, and so what we want to think about is what happens when we reach steady state, which means what happens when this laser is actually on and it's running, and you have your laser pointer, you've pushed the button, and say 1 second after you've pushed the button, this looks like a constant intensity laser. What are the equations then? Well, in that case, the rate of change of these populations is going to be 0. And so now we have the steady state population of n1, which is denoted by this bar, and n2, which is denoted by this bar. So now all you need to do is make the substitution, and we're going to look at just the threshold for population inversion. Later on, we'll get into when we're in the general case of having intensity. But for now, we're just going to say the threshold for population inversion is when this is just starting. So when this is just starting, we have no photons in the cavity, or very, very few photons in the cavity. So we're going to say that this is 0. And that gives us a very simple equation that the steady state upper state population is going to be the ratio of the pumping energy to this decay rate times the number of atoms in the lower state. Or since, as we said, nt is equal to n1 plus n2, then that means that the upper state population, steady state population, is going to be the ratio of the pump over the pump plus this decay rate times the total number of states. And of course, you just make the substitution for n1, and you get that the steady state solution for the ground state is going to be this decay rate over the pumping rate plus the decay rate. And the steady state population difference, of course, is n2 minus n1, and we need to have population inversion. And so we can only get population inversion when we have n2 minus n1 is p, the pumping rate, minus this decay rate, gamma 21, over the pumping rate plus gamma 21 times the total number of states. So the total number of states is just some number. And so in order to have population inversion, we need to have n2 greater than n1, and that's what's required for this laser to work. And so that means we need to have the pumping rate has to be greater than this decay rate here. Okay, so that's a requirement for 3-level lasers. All right, so remember that. Now for 4-level lasers, we end up with 3 differential equations because, again, we're going to assume that the rate of change of this population is basically 0. And so now we go from the 0th state to this 3rd state, and then it quickly decays to this 2nd state. And then this 2nd state is going to be, the pumping rate times this ground state minus this decay rate here, and of course any stimulated emission. So that's going to be, the stimulated emission is the sigma phi n2 minus n1. So it's a number of photons in this cavity. And the population in n1 in this short-lived first state is going to be, of course, how fast we decay from this first state down to the ground state, plus also, but we'll add population to the first state when we decay from the 2nd state down to the first state, and we also gain population in this first state from stimulated emission, from this absorption cross-section times the population difference. And the total population will be the sum of these 3 states. Again, we approximate that this upper state is close to 0 because it's such a short-lived state. Okay. Oh, right. And so one thing you might be wondering is, well, if these are fast states, why do we even take these into account? Well, we don't know what the pumping rate is yet. So we're going to assume that there is some population here, and there is going to be some population here. It's just that we assume that as soon as this goes to the third state, it immediately goes down to the second state, and so we're going to assume that there's no population in the third state. Okay, so again, we make the same assumption that in the steady state, we have the rate of change of the population is 0, because that's going to be the definition of the steady state, that nothing's changing anymore. And we're also going to make the assumption that we're at the threshold of this laser just working, so that means that we have almost no photons in this cavity, so let's assume that phi is equal to 0, where phi is the number of photons. That gives us 3 steady state population values. They are, the denominators are going to be the same for all 3 populations. We have the rate of change from 2 down to 1. We have at times the pumping rate. We have the decay rate from 1 down to 0 times the pumping rate. And we have the decay rate of 2 down to 1 and 1 down to 0. So that's the denominator for all these states. But for the 0 state, it's going to be how fast we decay from 1 down to 0 and how fast we decay from 2 down to 1. For the first state, it's going to be how fast we decay from 2 down to 1 and how fast we can pump back up to 3, which effectively goes down to 2. And for the excited state N2, it's going to depend on our pumping rate up to there, and then also how fast we decay from 1 to 0, which is kind of interesting because we don't actually take into account this gamma 2-1 transition. So we want population inversion, and so the population inversion is N2 minus N1. So these are the 2 states that we care about because that's the laser transition state. So we care about transition state from 2 to 1. So that's why we're taking N2 minus N1 and not N1 minus N0 or something like that, because that's not the laser transition. The laser transition is 2 down to 1. So you take that difference, and what you get is still the same denominator, but you get the pumping rate times the difference of gamma 1-2 or 1-0 and gamma 2-1. Okay, now what that means is as long as you have some pump on, you'll always get population inversion if gamma 1-0, this decay rate, is greater than gamma 2-1. Okay, so that means if this is a long-lived state and this is a short-lived state, you don't need very much pumping. As soon as you pump whatsoever, you will always get population inversion. And so that means that the threshold for population inversion is going to be much, much lower for a 4-level laser than it is for a 3-level laser. And so that's why we're still interested in 4-level lasers, even though it doesn't seem like there's that much of a difference. It turns out that if you actually look at the differential equations that describe these transitions, the threshold for getting population inversion is significantly lower. And you can make the simplification that if this ground state N0 is approximately equal to the total population, and the population of this first state is approximately 0, then the difference of this population is actually just the pump over the pump plus gamma 2-1. And so let's compare that to the 3-level laser here, where we have the population difference is the pump minus gamma 2-1 over pump plus gamma 2-1, whereas here we have just the pump over the pump plus gamma 2-1. And so we don't have to take into account that pump minus this spontaneous emission rate. So that's why it's so much more efficient, which is why 4-level lasers are interesting. High power lasers will almost always be 4-level lasers. Okay, so just to finish up, we're going to finish up the week talking about saturation. So recall from previous chapter, we had a 2-level system where the rate of change of the population is given by the number of photons in the cavity, the difference in the population, and the absorption cross-section. So this is going to be stimulated emission and then plus spontaneous decay. And we have the rate of change of the second state is going to be the loss caused by spontaneous emission, because this is the absorption cross-section, and then the number of photons in the cavity times this population difference. And then we lose population in the excited state due to some spontaneous decay rate. Now, if you remember, gain is given by the absorption cross-section and then the population difference, and the intensity is the number of photons times the energy of each photon. So your daily assignment for Monday is to go from these equations here down to equation 4.1.1, which are these two equations here. You find that, again, in the steady state, that's when the population doesn't change. So you set this equal to 0, that then you find what the value of n2 is and the value of n1, and you get that n2, the upper population in the steady state, it's going to be 1/2 the intensity divided by the saturation intensity plus over 1 plus the intensity over the saturation intensity times the total number of states. And n1, the steady state population, will be 1 plus 1/2 I over I saturation over 1 plus I over I saturation times the total number of states. Where the intensity, the saturation intensity, is this decay rate times the photon energy over 2 times the absorption cross-section. So if you don't understand how we got this, that's going to be your daily assignment for Monday. But this will be useful when we talk about small signal gain and saturation on the next slide. So let's talk about a 3-level laser. So understanding this will also help you for your weekly assignment. The 3-level laser, we just have these two different equations. Your daily or your weekly assignment will be solving this for a 4-level laser. So you have to go back to those different equations we had before. So for a 3-level laser, we have these two differential equations. So the rate of change of the ground state is given by, we lose ground state population by pumping, we gain ground state population by spontaneous decay, and we gain ground state population by stimulated emission here. And then we, the rate of change of the population, the excited state population, is we gain population by pumping from the ground state, we lose population in the upper state by spontaneous decay, and we lose population by stimulated emission. So again, we want to look at this in the steady state. So we set the rate of change equal to 0, and we get, with a little bit of math, it's exactly the same math that you did for the previous part, that the difference in the population, n2 minus n1, is going to be the pumping rate minus the spontaneous decay rate over the pumping rate plus the spontaneous decay rate plus 2 times sigma phi. So the difference between this and what we had previously is that now we're taking the stimulated emission into account. So what happens when we don't have small signal gain, or what happens when we do have a lot of photons in the cavity? So when we have a lot of photons in the cavity, it looks exactly like it is before, but we have this denominator that includes a 2 times the cross-section times the number of photons. So now we can, from the definition of the gain from before, we get that the gain is going to be this absorption cross-section times the pumping rate minus the spontaneous decay rate over the pumping rate plus the spontaneous decay rate plus 2 times this absorption cross-section times the number of photons times the total number of states in the system. Now, if you define your gain, your small signal gain, like what we had done here before, that we have P minus gamma 21 over P plus gamma 21. When there are basically no photons in the system, then if we define our small signal gain as this absorption cross-section times this pumping rate minus our decay rate over pumping rate plus our decay rate times the total number of states, then what we can do is change this to 1 plus phi over the saturation photon rate, or photon numbers, or the small signal gain over 1 plus the intensity over the saturation intensity. So the saturation intensity is given by the photon energy over 2 times the absorption cross-section times the pumping rate plus the spontaneous decay rate. Okay, and that ends up, that wraps up our chapter 4 for us. And so I skipped over a lot of the math for this. A lot of it's very similar. It is going to be on your daily assignment, and using this math will be your homework assignment. So hopefully by next week you'll see where this math comes from. The main thing is that what we have here is that this gain is actually going to be dependent on the intensity. So what that means is when we have almost no photons in the cavity, we have this gain here, this G naught, and this is a small signal gain. And so that means that we have this exponential increase in our photon rate. But eventually, of course, we can't amplify our laser an arbitrary amount. Of course, when you're holding your pen laser, it reaches some steady state. And that's by definition, we don't have this exponential increase in the number of photons anymore. We have some steady state. At this point, the intensity has saturated. And when this intensity is saturated, that means this gain has reached this kind of steady state gain. And that's when you have this, when the intensity is at some maximum value here. And so your homework assignment will be to understand what the dynamics of this are. And so we'll discuss this a little bit next week, but this pretty much summarizes covering chapter 4.